Okay. So let us start. So the principle of virtual work. So as I told you, so this is actually one fundamental principle, so which we can make use to find out the unknown forces in any structure which is under equilibrium condition, right? Now the principle of virtual work. So first actually we will derive what is the necessary and sufficient conditions for the principle of virtual work, and then actually we will try to state that. Just you note down the statement. So the necessary and sufficient conditions the necessary and sufficient condition that a particle or a rigid body acted upon by a system of coplanar forces be in equilibrium is that the algebraic sum of the virtual works done by the forces during any small displacement consistent with the geometrical conditions of the system is zero. To the first degree of approximation. Got it? So this is the principle of virtual work. So this is the statement which you can make a note of it. So as long as the system is under equilibrium condition, if you give any small displacement, it will come back to its original position. So that small displacement, whatever we are going to give it, is called as a virtual displacement, because actually we are trying to imagine that there is a displacement that went on the system, and then it will again come back to its original position. So because of that, actually essentially there is no work done, so which we call as the virtual work, right? So it is interpreted as there is some work done, but ideally there is no work done. So this is the principle of virtual work, right? Now here actually when there is a small displacement that was given, so then actually so f of x is displaced to a position of x plus delta x. So this is there is some extra statements consistent with the geometrical conditions. Consistent with the geometrical conditions, we mean, suppose actually if you take any particular structure, if you give displacement to one particular part of this structure, then it will try to influence the other parts as well. So it has to be consistent with geometrical conditions. That means suppose if I take one structure like this, now if you try to push this edge up, then actually it will try to push this one and this one also, right? So that's why it has to be consistent with all the geometrical conditions of this structure. So that is one important fundamental statement. Now actually, if there is a linear displacement, that means actually if you push it, then actually it might be pushed to the upwards, right? So there might be some kind of linear displacement or non-linear displacement also can happen. And so to be specific, we are generalizing the statement. So to the first degree of approximation. What do you mean by this first degree of approximation is, if the displacement is a function of x plus delta x, so where x is the displacement which went to a change of x plus delta x. Now actually on this particular function, if you operate it, so based on the Taylor's expansion, this is going to be f of x plus delta x into f dash of x plus delta x whole square by 2 factorial into f double dash of x plus up to infinity. Like this actually we can expand with the help of the Taylor's expansion. Now in the Taylor's expansion, if you notice, so this is the first degree of approximation. You can ignore all this kind of changes for the function f that was coming just because of the change in the displacement from x to x plus delta x. So this is what is the another statement. Though we have a non-linear displacement, still you can neglect all the non-linear displacements taking the first order approximation like this. So this is a more generalized statement what he has given, but we don't need to be worried about all these things. So we are very specifically dealing with only the linear cases. Got it? But as a statement, it has to be completely and comprehensive. That's why it was given all the aspects of it. Got it? You can note down this. So the necessary and sufficient conditions for the virtual work is, suppose on a body, if there is a displacement, so let the displacement be let there be a displacement of a body from P to Q, which makes a displacement of dr, which is given as u plus e cross r. So this was actually I have discussed yesterday. So dr is equal to u plus e cross r. Now the work done during the displacement w is equal to f dot dr. Now this w can be written as f dot u plus e cross r. So this is the work done, right? So in this case actually, so we have simplified this into f dot u plus e dot g. So this is how actually we can finally bring in. So this is the total work done, because actually any system of coplanar forces we can bring into a system of forces acting at one point along with a couple of g. Even here also this is, so E dot, if you take it, F cross R is nothing but G. Got it? So that's why actually, so F dot U plus E dot G is the total work done. So let dr be the virtual displacement. Dr be the virtual displacement, then the virtual work will be 0. Right? So virtual work is going to be 0. Hence, W is equal to 0, assuming the system of forces are under equilibrium condition. Right? So then actually, so F dot U plus E dot G equal to 0. So this is the principle of virtual work, and this is the necessary condition. Right? So this is the necessary condition. Now, if this system is having a zero work in total, then assume two different cases. So first you note down this. We are going to discuss separately these two. So F dot U plus E dot G equal to 0. Right? So if the total work is 0, then the sufficient condition should be the sum of all the forces should be equal to 0. And the sum of all the moments has to be equal to 0. Now in this actually, so if there be only linear displacement, then obviously F dot U has to be equal to 0. F dot U has to be equal to 0. As F and U are not perpendicular, because actually the resultant force is in this direction, then actually it can't move in this direction. It has to move only in this direction. That means this is a ruled out case. So the F and R values are always actually non-perpendicular to each other. Then the only possibility is F equal to 0. Then only actually this will be F dot U equal to 0. Now if you take the case 2, so this is case 1 and this is case 2. Assume that there is only movement, single movement without any resultant force. Then E dot G has to be equal to 0. So this is the sufficient condition. So as E and G are non-perpendicular again, then the only possibility is G equal to 0. So these are the sufficient conditions. That means the sum of both the works together has to be equal to 0. That is the necessary condition. And the sufficient condition is both R and G both has to be equal to 0. This is the sufficient condition. So there are three different conditions. This is equation number 1, and the other one is R equal to 0 and G equal to 0. So these are the three different conditions. Got it? So these are the necessary and sufficient conditions for the principle of virtual work. I hope you understood this concept. Okay. Now we'll solve some of the problems based on this understanding. So this is a simple concept. So the concept says that give you a virtual displacement and then try to find out the work and equate to 0 and find out the unknown forces. There is only one kinds of problems you can expect in this, that too mostly the rhombus case. So because that is easy to calculate. Note down one problem statement based on this. Five weightless rods of equal length are jointed together so as to form a rhombus. ABCD with one diagonal BD. With one diagonal BD. If a weight W be attached to C, if a weight W be attached to C, and the system be suspended from A, show that there is a thrust in BD equal to, show that there is a thrust in BD equal to W by root 3. So this is the problem statement. Read the statement carefully. Five weightless rods of equal length are jointed together so as to form a rhombus ABCD with one diagonal BD. If a weight W be attached to C and the system be suspended from A, show that there is a thrust in BD equal to W by root 3. Now here there is a rhombus. So the fundamental property of rhombus is it will be having equal side lengths and the diagonals are perpendicular to each other. That is a property of a rhombus. So this is a rhombus. It makes an angle of 90 degrees here. And then these four lengths are equal to each other. So this is A and this is B and this is C and this is D. Right? And then five rods, equal length rods of weightless are jointed to form a rhombus. Now actually to form this rhombus actually we need only four different sides. But actually one side he explicitly mentioned that BD is also the rod. That means this is not the rod and this is how the structure is. Right? So this ABCD along with BD, five different rods are there. All are of equal length and no weight for each of the every rod, right? So now actually if you notice, if it is suspended at this particular point and a weight is attached to C of magnitude W. So there is a weight that got attached to C and it is suspended from A. And then obviously, if you do this activity, if you don't have this BD rod, then actually automatically these two will come together and jointed, right? So it will be as if like it is a straight line, if this rod is not there. So to withstand that force, right? So there is a rod that got supported here. Obviously, if the weight that is attached to this particular point C, then automatically it will try to push this rod like this. If it is trying to push the rod, there will be a counter force that is going to be developed, right? So that counter force is nothing but this directional force. And this is what we call as the thrust. And this thrust value, so this is T. So this thrust value, he asked us to prove that it should be equal to W by root 3. So if you apply more weight here, then the more thrust will be developed. If you apply less weight here, then the less thrust will be developed here, right? So there is a relation between this T and W. So he asked us to prove T is equal to W by root 3. Now here actually we can apply the principle of virtual work now. Now here, if you notice, so if you draw a straight line like this, then it makes an angle of theta here. Obviously it will make an angle of theta because these two are the symmetric triangles. So the same structure whatever is there to the vertical line, the same structure is on the right hand side as well. So if it is supported at from A, if you attach the weight at C, obviously this will be a straight line, obviously, right? So this will be a straight line which will be exactly perpendicular to this horizontal line because this support and this weight has to be on the same line always because of the gravity, right? So if it is on the straight line, then obviously it has to make an angle of 90 degrees, being this is a rhombus, right? So now actually how to apply principle of virtual work here. So principle of virtual work says that you apply a virtual displacement to this particular structure, then try to calculate the work and try to equate that to 0. Now applying a virtual displacement. So let us see. Now A is a fixed point because it can't be moved because this is supported from this location. But this can be moved. So you can lift up or actually you can move like this. So any kind of displacement you can give to point C. So that is, suppose if I push this up like this, then actually there will be a change in the angle automatically, right? Yes or no? If I try to push this particular point C a little upper by fixing the point A, then obviously there will be displacement changes or actually the angle is going to be changed at both the cases, right? Yes or no? Right? Now this angle is going to be changed. Now actually, so during that situation, there will be a supporting rod in between these two. Now what we will do is, first you remove this rod and then try to replace with the corresponding thrust at this location. So this is how you can replace it. So this is T and this is T and this is the vertical line. This angle is theta and this angle is theta. Now actually you have given some vertical thrust. So just move this like this. Automatically these two are going to be moved in this direction. So this is the movement. So there will be a change in theta from theta to delta theta. So there will be a change. Now we will try to calculate these changes. Now actually there will be a change in this direction obviously and there will be a change in the vertical position also, right? So vertical direction also there will be a length change and the horizontal direction also there will be a length change. Now in the vertical direction there is a weight that is acting downwards. In the horizontal direction there is a tension that is acting outwards, right? Now here we will try to calculate. Let us say this length is of magnitude 2a. So this is 2a and this is 2a and this is 2a and this is 2a because L is equal to 2a is the length of the rod. So equal length rods, right? So that's why actually every length is taken as L, and which I said that it is equal to 2A. So just a random introduction of A constant, nothing more than that, right? So if you push a little upper, then it is making an angle of theta, right? So if it is making an angle of theta, then this height is going to be total height. So this is point A, and this is B, and this is C, and this is D. So AC is equal to, I call this point as O, then 2 times of AO. So 2 times of AO, and then this is going to be, AO is equal to 2 times of 2A cos theta. So that is AC. So this length actually you can say as, this length you can make it double so that you will get the length of AC. So this AC length actually you can calculate from AO. AO is equal to 2A times of cos theta, because this is making an angle of theta with the 2A length. And then this length, this BO. So BO you can calculate as 2 times 2A sin theta. BD you can calculate as 2 times of 2A sin theta, right? So you have calculated this length and you have calculated this length. Now for the vertical force, there is a weight that is acting like this, and for the horizontal force, there is a thrust that is acting at the outward direction like this. Now here, this displacement, there is a change. So this is, initially it was 4A cos theta, this is 4A cos theta, and this is also 4A sin theta. Now there is a change in this 4A cos theta and 4A sin theta because of the virtual displacement that was given. That means you can take the derivative of this with respect to theta, which is going to the virtual displacement. So virtual angular displacement, you are going to calculate it here. See this. So total virtual work is given as, so total work because of this change, right? So tension multiplied by the displacement. So tension, so displacement. So what is the displacement? Total we have. So this length is BD, actually we have calculated as 4A times of cos sin theta. So BD length is 4A sin theta. Now there is a virtual displacement that was given. So because of the virtual displacement, so what is the essential change in the displacement we have? What is the change in the displacement? There is nothing but the derivative of this particular one, right? So that is 3 times of derivative of 4A sin theta. Can I write this way? Got it or not? Tension multiplied by the displacement. And displacement actually directly we don't know. So because of the virtual displacement, whatever we have given, right, there will be a change in the displacement. That's what we call as the D, derivative of. Derivative is nothing but the change. So D of 4A sin theta is nothing but the displacement that happened for this particular length of BD. Understood or not? Is this understood? Because this is the methodology we are going to adapt for all the problems. So tension multiplied by the change in the displacement BD. So D of 4A sin theta plus one more force that is acting, which is downwards. And for this actually initially it was AC. Now there is a change in the length of AC as well. So that is weight multiplied by D of AC. So this has to be equal to 0. So this is the total work done, which we will be equating to 0, because after giving the displacement, it is going to come back again. Hence, the virtual work is going to be 0. So there are two different forces. All the rods are actually of weightless. Hence, you don't need to consider the weight of any rod. And there are external two forces. One force is the external weight that is acting downwards, and the internal thrust that is going to be developed because of this particular weight. Now, these two are only the responsible force components that we have it now. Now, in this direction, we will try to calculate the displacement change. And in this direction also, we will try to calculate the displacement change. So, both sum has to be equal to 0 as per the principle of virtual work. So, that's what we have done. So, T times of derivative of 4A sin theta plus W times of derivative of 4A cos theta has to be equal to 0. From there, we will be able to calculate the t value. Got it or not? Understood? Understood? Okay. So you can note down this. So I'm going to further move on this. First, you note down. So t times of derivative of 4a sin theta plus w times of derivative of 4a cos theta. So this is the change in the displacement. It has to be equal to 0 as per principle of virtual work. Now here, so t times of derivative of 4a sin theta. So 4a is a constant and then derivative of sin theta is cos theta, and then omega into 4a is a constant, derivative of cos theta is minus sin theta, and this is equal to 0. That means 4a, if you take it out, t cos theta minus w sin theta equal to 0. It implies t cos theta equal to omega sin theta, or t is equal to omega tan theta. So this is the tension and the weight relation. Now initially, when the body is under equilibrium condition, if you notice, this length is 2a and this length is 2a, and even this also the rod again. So initially this structure was built with 5 different rods. So this is one rod, this is one rod, this is one rod, and this is one, and this is one. So these 3 actually are forming an equilateral triangle. So being triangle ABD is an equilateral triangle. So if it is an equilateral triangle, obviously theta is equal to 30 degrees, right? Pi by 6. Why? Because 2 theta equal to pi by 3. So 2 theta is equal to 60 degrees. Now we need only one angle theta. So this angle is pi by 6. That means it is making an angle of 30 degrees initially when the body is under equilibrium condition. Now during that situation, so this is a general relation for whatever may be the angle theta, this is always equal to t value w times of tan theta. Now initial condition, w times of tan pi by 6 is equal to w by root 3. Got it? Understood? Okay, great. So you can note down this and we'll solve one more. Four rods of equal weights. 4 rods of equal weights. So earlier problem statement, actually the rods are having no weight. Now actually equal weights. W form a rhombus ABCD. Form a rhombus ABCD with smooth hinges at the joints. With smooth hinges at the joints. The frame is suspended by the point A. The frame is suspended from point A. And a weight W is attached to C. And a weight W. So this is capital W. Earlier one is small w. Is attached. To avoid the confusion, I call this as P. Is attached to C. A stiffening rod of negligible weight, a stiffening rod of negligible weight joins the middle points of AB and AD. Joins the middle points of AB and AD. Keeping these inclined at alpha to AC. Keeping these inclined at alpha to AC. Show that the thrust in the stiffening rod is, show that the thrust in the stiffening rod is 2p plus 2w, sorry, 2p plus 4w times tan alpha. So this is what actually he asked us to prove. Now this is more or less exactly the similar problem what we have done earlier, but few differences are there. So those differences are, he has given the weight of the rods only for the 4 rods, but there is a 5th rod which is weightless. That is one scenario. And then the angle alpha instead of theta what he has given. So that is, again this is the same rhombus, and this is AC. So there is a weight that got attached at this location of magnitude P, and this rod is having a weight of W, and this is having a weight of W, and this is having a weight of W, and this is also having a weight of W. So 4 different W's are there. Now this is also a rhombus, hence actually I'll draw it again. So weight of magnitude P that got attached at the bottommost point C, and this is jointed at this location. So there is a support that was given there. Now it is making an angle of alpha, and this is also making an angle of alpha. Now actually he didn't talk about this particular length. He didn't say that whether this length is equal to the side length which was there in the earlier case. Now actually it's anyway not equal. So rhombus can be any shape like this. So even this also a rhombus. As long as these two are perpendicular, this we can call as rhombus irrespective of this diagonal length. So this case actually what he has given is, this is the middle point of AB and this is the middle point of EAD. So I call this as E and I call this as F. Now the support is at this location now. Support is at this location now. Now there will be a thrust at this location obviously, right? And there will be a thrust. And this thrust relation actually he asked us to find out. Now exactly the same procedure you try to apply and then try to solve it. Now give a virtual displacement at this location. Now try to calculate the, so in this particular direction there will be a change in the length, and in this direction also there will be a change in the length for EF. So first you identify the length of EF and you identify the length of AC in terms of alpha and apply the same procedure of the principle of virtual work what we have done in the previous case. You will be arriving at this particular relation. I am going to give you 5 minutes time, so try to solve this on your own. So one important understanding should be, being this is the midpoint, so that is, so AE is equal to BE is equal to AB by 2, and similarly AF is equal to FD is equal to AD by 2. So this is the midpoint. Now if it is the midpoint, obviously this point is also the midpoint of AO. So I call this as X. So AX is equal to XO is equal to AO by 2. So use these relations. So this length, right? So this length actually, so you can treat as 2A, so that this can be A and this can be A. Similarly, this is A and this is A. So from there actually you can arrive at the same situation the way we have done in the previous case. This length you calculate in terms of A and alpha, and this length also you calculate in terms of A and alpha, and then finally arrive at the length AC and EF. How to construct W? So W, right? So this is a weight actually which you can treat as if like it is acting at the center of gravity, right? So there is a W here and there is a W here and there is a W here as well. So 4 different W's are there. Now if you give a virtual displacement at this location, obviously there will be a change in the displacement of this particular point of application like this, and similarly for this W also there will be a virtual displacement in vertically upwards, and for this also there will be a virtual displacement vertically upwards and virtual displacement virtually upward, right? So all the 4 different W's actually are subjected to a displacement change, and even this P also is subjected to a displacement change. So see this is a single line problem. So now actually total how many forces are there? This P is there and 4 different W's are there, and there will be one thrust which is acting of horizontal direction. So this is the thrust direction. Now if you notice 4W, 1P and 1T. So total 6 different forces that are acting on this particular structure. Now when you give a virtual displacement at this particular point and every point is going to be moved. Now if you notice, so the height actually that it got incurred because of the virtual displacement that was given at this location will be subjected to the length of this particular length, right? So now actually if you notice the virtual work, after giving a virtual displacement at point C will be given by, now let us see what are all the forces lengths that are incurred in this. Now this length is A, and this is the midpoint of this particular structure, hence this length is A, and this is making an angle of alpha. Then AX is equal to A cos alpha, and EX equal to A sin alpha. But we need the displacement EF. EF is equal to 2 times of A sin alpha. So this is one displacement component that is responsible for the thrust T, and then we will take this particular force, that is P, and this length we need AC. So AC actually, this length we were able to calculate with the help of this formula, that is AX is equal to A cos alpha. So if this is A cos alpha, this is also A cos alpha. So if the entire length is 2 times of A cos alpha, this will be again 2 times of A cos alpha. In total AC is equal to 4 times of A cos alpha, correct? So AC is equal to 4 times of A cos alpha. Got it? So AC also we have got for this P. For T we have calculated EF. And then for all other 4 forces of W, we have to be calculating the virtual displacement. Now to calculate the virtual displacement, if there is a little displacement, there will be a change in this particular displacement to a little high, right? Now that length is going to be 2A times of, so this vertical length whatever it is there, right, it is going to be changed a little high. That means it is responsible for AX. Sorry, it is responsible for AO. So because actually this structure is moving a little high like this. Now this length actually will decide how much it has to be going upwards, right? So obviously this W is subjected to, so W is subjected to a length of 2A cos alpha, right? So 2A cos alpha is this length. So for each rod actually there will be a vertical displacement obviously. This vertical displacement is responsible for this one. So for these two structures this length, for these two structures this length, but both are of equal magnitude. Hence actually it is making a displacement of derivative of 2A cos alpha. Got it? Understood or not? Understood? I think so. It is not visible. First you note down this. I am going to erase it and then actually I will rewrite it. So till this point 4A cos alpha you note down. So bottom line I am going to rewrite again. See this. So for this W to move a little high, right? So because the displacement was given at this location. So this is moving because this is stretched onto the length of BC. It is at the middle point. Now this movement will cause this particular length to move a little high. Now if that is moving a little high, so this length actually will decide how much length actually it has to go up. That means if you notice this vertical height whatever it is going to be there, that is going to be changed for this particular W. Got it or not? So this length projected onto this line is nothing but 2A cos alpha is going to be changed for this particular W. Got it? So because there is only one vertical virtual displacement what we have given. So total displacement. So AC is 4A cos alpha and AO is equal to OC is equal to 2A cos alpha responsible for W. And this is responsible for P. And EF is equal to 2A sin alpha responsible for T. So the virtual work is given by T times of derivative of 2A sin alpha plus P times of derivative of 4A cos alpha plus 4 times of W. So because 4 different W's subjected to the same length, derivative of 2A cos alpha is equal to 0. So this is the principle of virtual work. Now if you simplify this, T times of derivative of 2A sin alpha, 2A is a constant and derivative of sin alpha is cos alpha into d alpha plus P times of 4A into derivative of cos alpha is minus sin alpha into d alpha plus 4 times of W times of 2A into derivative of cos alpha is minus sin alpha into d alpha equal to 0. Now this d alpha will cancel out and then this 2A and out of this 4A there will be only 2 left over. Yeah. So T times of cos alpha minus 2P sin alpha minus 4W times of sin alpha equal to 0. So T cos alpha minus 2p plus 4w times sin alpha equal to 0, or T equal to 2p plus 4w times of tan alpha. So this is the thrust that is going to be developed because of this particular structure. Got it? See this. So now actually the vertical position of this W is at this location, right? So which is the center of gravity. Now actually, if there is a virtual displacement that was given at this particular location, the center of gravity of this particular W is going to be shifted, right? How much it is going to be shifted? So because of the vertical location of this particular body from here to here. So because this particular structure is moving a little higher, that means the Y location is getting changed without changing the X location. Now if the Y location is getting changed, then this particular length initially which was at this location, now actually this is moved a little high like this. Now initially this is the end point and this is the start point, and the same structure actually the Y location is this one to this one. Now this is going to be changed because of the movement of this particular W movement in a vertical direction. Got it? Understood or not? Vishal? Yeah. So this is how actually the principle of virtual work we can make use to find out the unknown forces like this. So only thing is the straightforward relation. So the virtual work actually it will be straight away equated to 0, assuming that there will be a little displacement that was given. So ideally it is not there, or actually in reality there is no displacement. We are assuming that there will be a little displacement given at any location of your own interest, and based on that, depending upon the geometrical conditions, we are trying to calculate because of the movement of the virtual displacement. So there will be displacements in the entire structure, and each and every structure we have to be identifying and calculating the displacement, and correspondingly we will be calculating the work by multiplying the displacement change with the force, so that you are going to get the virtual displacement or the change in the work. So that change in the work actually we are equating to 0 to find out the unknown forces, right? So this is a kind of a catalyst for us. So this catalyst actually is responsible for identifying the unknown force. Got it? Yeah. So what is your question? If there is one more rod in the middle of BC and DC, yeah, BC and DC, even here also you have to be calculating, right? So if BC and DC actually, if there is one more rod, there will be one more thrust here as well. Now actually if you try to push a little upper, then there will be a force that is dragging towards this direction, even here also towards this direction. This is tension T1 and this is tension T2, depending upon the strength of this particular rod in between whatever is attached. So the same methodology what we are going to adapt here. So here T1 and T2, there will be two different variables that we are going to get it. Got it? Understood, Vishal? Yeah. So this is about the principle of virtual work. So we are done with this. So I'll be giving few problems based on this understanding. So maybe actually you can try to solve those problems. In the next class, I'm going to start with the stability of equilibrium. That will be the last topic. Got it? Yeah. So till then, yeah, good night. Thank you.